it would be much more. There are many, many, many more universes like this than this very peculiar one that we actually have. Now, you could say this is an act of God or something like that. I prefer to take a different position, which is that there is some reason from physics why it had to be like this and not like that. Now, I used to say, just as a hypothesis, the thing I used to call the Weyl curvature hypothesis, named after Hermann Weyl, a very great mathematician, and he used the notion of curvature called the Weyl curvature, which in conformal geometry is the curvature which you can have in conformal geometry. But I said, okay, for some reason we don't know, the initial universe had to have this Weyl curvature 0. And that's a very special condition. You can work out the probabilities. This is using the famous formula of Bechtstein and Hawking, which tells you how much entropy there is in a black hole. And that entropy is absolutely huge. If you take this collapsing universe, which I predicted here, the congealing black holes will give you a measure of that entropy. And that tells you how much more likely that universe would be than the one we actually have, if it was randomly chosen. How much more likely is that? Well, the universe we see would have been something like an improbability of 1 part in 10 to the power 124. Now you see that's 2 exponents. If I wanted to write the number down, which is 0, 1, 0, 0, 0, 0, 0, 0, it would not be nearly enough room in the observable universe to put a 0 on every proton. It wouldn't be nearly enough room. So we don't do it that way. We put another exponent there. So the number of zeros is already 10 to the 124. That's an absolutely huge number. So the unlikeliness of that universe, if it was just random, is ridiculous. Now, either, as I say, it was an act of God or something, or maybe there is some physical reason, and that physical reason has to be something. What? Well, for asking reason, let me just try to ask what the geometry looks like. Well, I say a Weyl curvature, but that's complicated because I would have to explain what the Weyl curvature is. It's fortunate that my colleague Paul Todd had a very nice way of saying it. He says, okay, no, you don't talk about Weyl curvature. You just say the condition is that if you stretch out the Big Bang, then it's the move. And you could imagine continuing this stretched out universe to something forward. So it's this thing which I indicated before. Where I said, suppose we stretch out the universe, it's a very strong condition. It's a very general condition. The squash of infinity, but the stretching out to make it a nice smooth surface, it's a very strong condition, but it's a very strong condition of just the kind you want to make the universe like the kind of universe that we have. That is to say, make the universe like this, and not like this. So that almost all possible universes would be this great mess at the beginning with no use at all, no selective law of thermodynamics, no universe that looks anything like what we have, a very small number of universes which look like this. It's just a hypothesis. So that is basically the hypothesis, which, what I call the Weyl curvature hypothesis, or the hypothesis that Paul Todd is making, which is that we can use this picture and it makes sense. Then beyond this is to say that the reason that we have to use this picture is because the reason is that there was a prior eon to us. I'm saying that our eon was not the beginning, it was still our eons. These eons went on before and before and before. I'm not saying it has to be that explanation. I'm just saying that it is an explanation. And it's the only cosmology I know of which actually faces up to this point. So although people may say it's a crazy scheme, and it is crazy in its way, I'm not saying that it's not crazy, but I'm saying that we need a crazy scheme because there is something peculiar about the initiative, isn't it? Okay. So that is a strong motivation for this. But before talking about that, I want to say about something about the physics of this. You see, why am I allowed these conformal tricks? Physically, why am I allowed to do them? I mean, I can do it mathematically, but why is it good physics? And the reason I'm saying it's good physics is because why do we believe in our metric structure of the universe at all? General relativity works extraordinarily well. The main reason it works extraordinarily well is that we have clocks which are absolutely extraordinarily precise. We now depend on it a lot when we drive our cars because the car has a GPS system, what sorts of other things, satellites, goodness knows what. The GPS system tells you where you are because there are these satellites in orbit around the Earth which are sending out very precisely timed signals. And the timing of these signals is that we use that to measure where we are. And that requires Einstein's theory. If you have Einstein's general relativity, you will get the wrong answer. You'll be out by a long way. In fact, a way which would be just very serious indeed. However, the theory works very well, and it works very well because there are such things as precise clocks. Now, why is that? Well, it depends on two of the most fundamental physical principles. One of these is Einstein's E equals mc squared. These are the two most famous equations of basic 20th century physics. Einstein's E equals mc squared, Max Planck's E equals h nu. I already said a little bit about this in the Planck radiation formula. This is frequency is proportional to energy. Einstein tells us that mass is proportional to energy. These constants, h and c squared. So if you put them together, you see frequency and mass are basically equivalent. So if you have a particle which has a well-defined mass, that particle is a clock, an extremely precise clock. Now, atomic and nuclear clocks, and these clocks don't ultimately they do depend. They depend on masses make clocks. You have to get the information up to make a good clock. But the basic point is that mass, any particle with a stable particle with a well-defined mass, is a clock. And so this is what gives us the measure of time, and this tells us what to give the metric of Einstein's theory. I told you about light cones. Here's a light cone. We need to add the clocks. Now, here I'm imagining two clocks, the brown clock and the green clock. Let's suppose they're identical clocks. They tick at the same rate, and as they go at different speeds, the ticks will trace out these bowl-shaped surfaces here, which tell us this is the first tick, second tick, third tick, and so on. And you would have this in the past too. So the point is that we have to not just have the idea of a cone. You see, where the cones are, that is the conformal geometry of space-time. You could squash the space geometry in this direction. As long as you leave the cones alone, this doesn't change the conformal geometry. But the metric geometry, that gives you the scale. And the clocks give you the scale. And I want to put this in terms of numbers here. You see, the conformal geometry, where the light cones are, I've shown you pictures of light cones and all that, that information is 9 of the 10 components in the metric. See, the metric, often written GAP or GIP or GEV or something like that, that is the metric which Einstein uses in his theory, has 10 numbers to define it at any point, 10 components. 9 of them, in other words, written the ratios in this sense, give you the light curve. That's almost all the information. The one more piece of information is this scaling. Now, I'm distinguishing these things from each other because different parts of physics are interested in the metric, not necessarily how this picture with the light curves. Now that is only giving the light curves. If we want the whole metric, then we need to put these surfaces in, which give us the 10th component. Now that Einstein needs all those components for his theory. But many parts of physics don't need this. In fact, it's really mass. Anything to do with mass, say, you need the scaling. But if we don't have mass, in particular if we have light, photons, all we need is that. That Maxwell's equations, which tell us how electromagnetic waves behave, electricity and magnetism, they don't need this, they just need that. So anything without mass doesn't need the scale, just needs the light curves. So, let's first talk about the Big Bang. When we get close to the Big Bang, the energy is so high that particles become, in effect, without mass. They become, in effect, massless. So that they might as well be massless. So right near the Big Bang, the physics which is relevant is simply the physics of massless particles, which is the physics of conformal geometry. So the stretching out of the Big Bang makes sense in terms of physics.
Actually,
Physical geometry, the conformal geometry is perfectly good geometry to talk about. I can see that something's not working.
yes.
There's no picture at the moment, but that's because there is no picture. Yeah. First of all, let me just say that black holes, see, the remote future, we have black holes, and the black holes will evaporate according to Stephen Hawking, and then we have a picture which will make sense for the remote future. So that's the eon we have here. That's the end of our eon here, and I'm trying to say this will match to the beginning of a new eon. And you have to make sure that the black holes will disappear, because according to Hawking, they evaporate away.
Yes.
And the question that we need to say here is, how does the second law of thermodynamics work in a cyclic universe? And maybe this would be one of the questions, because it would be a very reasonable question. If entropy is increasing, how can it keep increasing? And the argument is that when the black holes evaporate away, they swallow information. Now this is a big argument that people have in physics today, because they say, how can information disappear? Because we have fundamental laws in quantum mechanics which says that information cannot get lost. Now Stephen Hawking originally said that information is lost, and then he changed his mind and said it's not lost. And I think it was wrong to change his mind. He was right initially, and this is an indication that quantum mechanics is actually inconsistent with general relativity. And there are various reasons for believing this. And the point is that if you believe that quantum mechanics is completely true for black holes, or even for measurements, you see there's a big fundamental reason that quantum mechanics has its inconsistencies. And these show up when gravity is present. So we already see, in a black hole, information gets swallowed. Now, because information gets swallowed, this means that the definition of your entropy has to change. When black holes disappear, it's not that the entropy comes down, but you change your mind about what you mean about the entropy, because the degrees of freedom which are swallowed by the black holes are lost. And then your entropy in effect comes down. So you have a consistency with the second law, because every time a black hole disappears, your definition of entropy changes because you do not take into account the degrees of freedom which are swallowed by the black hole, and therefore the entropy you're interested in becomes small. So it never violates the second law, but it gives you a new definition of entropy every time your black holes disappear, and that gives you a consistency in this picture. I think it's an important point to make, because otherwise there is a clear problem with how the second law can make sense. But at this point, I'm happy to answer questions. If this other things come to light from the questions.
We will love to have that session. Okay. Thank you very much, very much. And everybody is very, they are clapping their hands. All are clapping their hands for seeing the most eminent scientist, physicist of this century, Sir Roger Penrose. And thank you very, very much for your enormous, energetic lecture for us.
Respected Professor Mahendra Muni, respected Mahavrati Gan, respected Anuvrati Gan, respected Shravak and my friends. I wanted to speak, I was allotted 20 minutes, but I am asked to finish in 15 minutes, so I would try my best to complete in 15 minutes. I would cut short. The science is wonderful, everybody knows, but it does not talk of peace. And peace is big necessity. Therefore, we need spirituality. And spirituality is based on the belief on eternal soul and karmic laws. Now, I skipped some part of quantum mechanics, but I want to say that quantum mechanics is the most minute and respectable area of science and physics. And many Nobel laureates have come from quantum mechanics discipline. And this quantum mechanics says that there is some kind of incompleteness, and incompleteness is revealed by the fact that there is acceptance of uncertainty principle. And this uncertainty principle in layman language, I would say, as if cashier is taking account, balancing the books, and he is missing one entry and books are not balanced. So this is what happening in quantum mechanics. And second point is same cause, same effect works in a probabilistic way in quantum mechanics. About the missing entry, there are books like The Ghost in the Atom. Can you imagine Cambridge University Press would publish a book like The Ghost in the Atom? It is because of missing entry. And in the morning also, one gentleman has spoken that now we think that there is something like soul and material description is incomplete. And many Nobel laureates support this. I am cutting my time, so I am not giving details of those Nobel laureates. And I want to quote that George Wald, medicine Nobel laureate, has used word Atman, essential self, ageless, imperishable. Ajar Amar, Atma ki baat, George Wald Nobel laureate bhi karte hain. He even says to the extent, thou art that Tattvamasi, that is the stuff. He uses the word stuff. Stuff indicates that the soul is real thing. It is dravya. It leads us to eternal dravya. So it is not only one Nobel laureate. There are many Nobel laureates. It is list of at least 27 in physics, chemistry, and medicine. And if I include other disciplines, it is a list of 50. I would name a few: Einstein, Planck, Schrödinger, Heisenberg, Millikan, Towns, Shallow, Phillips, Bragg, Marconi, Compton, Penzias, Mott, Rabi, Salam, Huish, Taylor, Carrel, Eccles, Murray, Chain, Wald, Ross, Barton, and his son Kohn Smalley, all these Nobel laureates of science say we are not materialistic scientists. We believe in something beyond material things. So, and now if you ask question to quantum science, what is official position about soul? Given three choice, we give three choice: yes, no, or science neither confirmed nor denied. Official position is neither yes nor no. Official position is science has not yet confirmed soul, but science has not yet denied soul. Now question arises, why scientists could not confirm the soul? I give 2 points. One is there is not much funding for soul in the science. There is funding for war and there is funding for other activities, but not for soul. And second point, very important point, our Jain scholars say, in Samaysar, persons of height of Acharya Kunda says, soul cannot be detected by any instrument. And I want to quote more about Samaysar. First, there are many persons who are not aware of Samaysar. Acharya Mahapragya has spoken, Samaysar is the most outstanding one.